last class we were discussing the high Peclet number convection dominated flow past a spherical particle. We had already done this for a flat surface. As we saw in a convection dominated flow, even though convection is large compared to diffusion, there has to be thin regions near the surfaces where diffusion is important, because the transport from a surface has to take place perpendicular to the surface, and that transport perpendicular to a surface cannot take place due to diffusion, due to convection. Therefore, transport perpendicular to the surface has to necessarily take place due to diffusion. Therefore, we will have thin boundary layers near solid surfaces in the limit of high Peclet number, where diffusion effects are important. That thickness of that boundary layer decreases as the Peclet number increases. The equations expressed in scaled form, when the coordinate is scaled by the boundary layer thickness, that equation is independent of Peclet number even as the Peclet number becomes very large. And therefore, within this thin region there is going to be a balance between convection and diffusion. We were looking at the flow around a spherical particle in the previous lecture, okay, in which the fluid was incident on this particle far from the particle, and as the fluid flows across, the concentration far from the particle is C infinity. At the surface of the particle, the concentration is C naught, which is different from C infinity, and therefore, there is diffusion taking place from the surface of the particle. The diffusion takes place from the surface, and the mass that is generated from the surface is swept backwards by the mean flow, the mean velocity, and that balance basically determines the transport rate from the surface. We had written down the balance equation, the convection diffusion equation at steady state. Of course, we need prescribed velocities for the fluid flow before we can solve the problem. Those velocities for a laminar flow were given here. Okay. We had scaled the velocities and got a convection diffusion equation. The velocities themselves are rather complicated in form. Okay. The velocities themselves are rather complicated in form. However, we are only interested in the flow field close to the surface of the particles, because we anticipate that the diffusion from the surface will be restricted to a thin boundary layer near the surface in the limit of high Peclet number. Okay. So, on that basis, we had actually expanded the velocities in a series around the surface of the particle. Okay. I had defined a coordinate delta y such that delta y is the distance from the surface of the particle, y is a number that is order 1, and delta is a boundary layer thickness. So, this was inserted into the equation for the particle, and I had done a Taylor series expansion in the small parameter delta. The radial velocity, the velocity normal to the surface, ended up being proportional to delta y the whole square. So, the velocity perpendicular to the surface goes as the square of the distance from the surface. The velocity parallel to the surface is linear in the distance from the surface. The latter is not surprising. The velocity at the surface itself has to be equal to 0. So, if I plot the velocity profile at the surface, the velocity has to be 0 at the surface because the particle is stationary. We are in a reference frame situated on the particle, in which the particle is stationary. Therefore, the surface of the particle is also stationary. Due to that, the velocity has to be 0 at the surface itself, and if the shear stress is non-zero, there has to be a linear increase from the surface. So, this is not surprising. The no slip condition implies that the tangential velocity is linearly increasing from the surface, and as I will show a little later, it also implies that the normal velocity goes as the square of the distance from the surface. Okay. And we had inserted this into the conservation equation, okay, in order to get a balance equation. Now, what we need to do is to get a similarity solution. and for that I have to define a similarity variable. Okay. The similarity variable I will define, okay. In this particular case, the streamwise direction is already dimensionless, it is already an angle, okay. And therefore, I can use that itself, okay, as a dimensionless measure of the downstream distance. Okay. Therefore, I can very easily define the similarity variable as r star minus 1 divided by this boundary layer thickness theta, okay, where r star is scaled by the radius of the particle, okay, and r star is equal to 1 is the location of the surface itself scaled by capital R. Okay. R star minus 1 is the distance from the surface, and that I scale by this boundary layer thickness delta, which has to be a function of theta. Okay. It has to be a function of theta because theta is already dimensionless. In the previous example, where I had taken the flow past a flat surface, the streamwise distance was a physical distance, it was the x location, and therefore, I had to search for a dimensionless representation of that distance. In this particular case, theta is already dimensionless. So, I could as well use that as a dimensionless parameter. Okay. So, when expressed in terms of theta, okay, this conservation equation, okay, basically becomes, okay, 3 by 2 into the Peclet number into minus cos theta. Okay. So, first I have to write down the derivatives, I am sorry. Okay. First I have to write down the equations for the derivatives. Okay. So, I have eta is equal to r star minus 1 by delta of theta, okay, which implies that partial by partial r star will be equal to partial eta by partial r star partial by partial eta, okay, which is equal to 1 by delta partial by partial eta. Okay. Differentiation using chain rule to express the physical coordinates in terms of this similarity variable. Okay. Okay. Similarly, okay, partial by partial theta is equal to partial eta by partial theta, okay, which is equal to minus of r star minus 1 by delta square d delta by d theta. And this I can re-express back in terms of eta, because eta is r star minus 1 by delta. So, I can write this as minus eta by delta okay. So, those are the derivatives in terms of the similarity variable. Okay. And now, I can take this scaled equation. I know that streamwise diffusion can be neglected, and the cross stream diffusion term will just be equal to 1 over delta square, okay, partial C by partial delta. Okay. So, therefore, if I express this back, okay, my original equation was u r partial C by partial r plus u theta by r partial C by partial theta, okay, is equal to d by r partial by partial r. Okay. I had already scaled the equation, so I should not have a diffusion coefficient here. Okay. This should just be 1 by r d by okay. And there is a Peclet number here which emerges from the non-dimensionalization. Now, expressing this equation, the balance between convection and cross stream diffusion in terms of the similarity variable, okay, I am going to get, okay, u r, if you recall, was minus 3 by 2 cos theta into delta square eta square. Okay. If you go back to our original expansion, okay, I had got minus 3 by 2 delta square delta y the whole square. So, y in this case is just the same as eta, it is a dimensionless coordinate. So, u r is equal to minus 3 by 2 cos theta delta y the whole square, and u theta was 3 by 2 sin theta into delta y the whole square. Okay. Into partial c by partial r. Okay. This will be 1 by delta partial c by partial eta. Okay. So, this first term here is the radial velocity, and the second term here is partial c by partial r. Okay. First term is the radial velocity, the second term is partial c by partial r. Okay. Then u theta, which was plus 3 by 2 sin theta delta times eta. Okay. That was the velocity. Okay. Okay. And I have to divide that by r star, which is 1 plus delta eta. Okay. Partial c by partial theta is now given by this term here. Okay. So, therefore, I get this multiplied by minus eta by delta d delta by d theta partial by partial eta. Okay. And this second term here, as we saw, is 1 by 1 plus delta eta the whole square. Okay. 1 by r d by dr of 1 by r square d by dr of r square dc by dr. And whenever I have 1 plus delta eta, I know that delta is small. So, I can always neglect delta in comparison to 1. Okay. And putting it all together, okay, I will get a minus 3 by 2 Peclet number. Okay. The theta dependencies. Okay. First, I have cos theta delta. Okay. You can see that I have delta square. Okay, and 1 over delta. Okay. Then I have minus, okay, plus, okay, sin theta, okay, delta into okay. In this second term here, these deltas will cancel out. Okay. These deltas will cancel out. So, I will just get sin theta into d delta by d theta. Okay. So, that is the dependence on the theta coordinate. How about the dependence on eta? Okay. I have 1 eta square here, I have 1 eta here and 1 eta here. So, both terms are multiplied by eta square. Okay. So, this becomes eta square dc by d eta. Okay. There should be a c star here. Okay. This is the left hand side. Okay. On the right hand side, I have 1 over delta square d square c by d eta square. Now, I can collect terms, multiply throughout by delta square, and I will get minus 3 by 2 Peclet number cos theta delta cubed plus sin theta delta square d delta by d theta eta square dc by d eta is equal to d square c by d eta square. Okay. So, this is the equation expressed in terms of the similarity variable. Okay. For this equation to have a similarity solution, this entire function, which is a function of delta, has to be a constant. For the equation to have a similarity variable, this entire function has to be a constant. That constant can be any value. The solution for a given constant in terms of eta will depend upon that constant, but when I express it back in terms of r and theta, it will no longer depend on that constant. Okay. So, from the similarity condition, I get two equations. Okay. The first one is the for the boundary layer thickness. Okay. The first one is that 3 by 2 Pe into cos theta delta square plus delta cubed, I am sorry, plus sin theta delta square d delta by d theta. Okay. This has to be any constant. Okay. Without loss of generality, I can set this equal to 1, okay, because the final solution will not depend upon the particular value of the constant. Okay. The second equation is the equation for the concentration field in terms of eta, and that is minus eta square dc by d eta is equal to d square c by d eta square. Okay. So, these are the two equations that have to be solved. Okay. Notice that the equation expressed in terms of the concentration field here, okay, is identical to the equation that we had got previously for a flat plate. Okay. If you recall, we had solved this equation for the flat plate. The equation for the temperature field was basically minus eta square dt by d eta is equal to d square t by d eta square, and we had got the solution here. Okay. That solution turns out to be exactly the same in this problem as well, because the equation for the concentration field in terms of the similarity variable is identical to what I had for a flat plate. Therefore, the solution is the same. What changes is the solution for the boundary layer thickness as a function of the downstream coordinate. In the previous case, that boundary layer thickness was in terms of the downstream distance x. In the present case, it is in terms of the angle theta. So, that is the only thing that changes. So, we now have to solve these two equations. Okay. The first one is 3 by 2 Peclet number into cos theta delta cubed plus sin theta delta square d delta by d theta is equal to 1. Okay. So, that is the equation for the boundary layer thickness. The second equation is for the temperature field in terms of the similarity variable, minus eta square dc in this case This equation we have already solved. We know what is the solution. Okay. With boundary conditions C star is equal to 0 as eta goes to infinity, and C star is equal to 1 at eta is equal to 0. Eta is equal to 0 in this case corresponds to the surface of the sphere. At that point, C is equal to C naught, therefore, C star is 1. Okay. That is the inhomogeneous boundary condition. C star is equal to 0 at infinity means that the concentration goes back to C infinity far from the particle. This equation can be solved. Okay. We have already solved it. The solution was C star is equal to 1 minus 3 power 2 by 3 by gamma of 1/3, okay, integral 0 to eta d eta prime e power minus eta prime cubed by 3. Okay. And the flux at the surface at eta is equal to 0. Okay. Okay. We had got that as plus d into C naught minus C infinity by r, okay, into 3 power 2 by 3 by gamma of 1 by 3. Okay. So, those were the equations that we had got for the flux and for the concentration field. Okay. Okay. This was the equation for the concentration field, okay, and the present solution is exactly the same as this one, except that C star is substituted for T star, and we had got an equation for the flux as well. Okay. Qy at y is equal to 0, okay, k into T naught minus T infinity by delta. times 3 power 2/3 by gamma of 1/3. Okay. So, I should put in here r delta of theta here, my apologies, because the boundary layer thickness and all length scales in this problem have been non dimensionalized by r. So, the actual physical boundary layer thickness is r times delta. Okay. So, that I have to substitute for the delta in the previous case. Okay. So, this solution is the same. Now, I have to solve this first case. Okay. How do you solve this? Okay. The way to solve this, okay, so first thing we can simplify this 3 by 2 Peclet number into cos theta delta cubed plus sin theta by 3 d delta cubed by d theta is equal to 1. Okay. This can be solved by integrating factors. I can write down this parameter delta cubed, okay, is product of a homogeneous part plus a inhomogeneous part. Okay. Okay. This homogeneous part satisfies the equation, okay, the homogeneous equation, that is cos theta delta cubed plus sin theta by 3, okay, the homogeneous part, d delta h cubed by d theta is equal to 0. It satisfies the homogeneous equation. Okay. This I can solve. Okay. So, delta h cubed is equal to, I am sorry, and this of course you can integrate, okay, d delta h cubed by is equal to minus 3 cos theta by sin theta, okay, which will give us delta h cubed will be equal to c by sin cube theta. Okay. So, that is the solution of the homogeneous equation. Okay. So, the first part will just be equal to c by sin cube theta. Okay. So, let me write this. Okay. I should write this as a sum of a homogeneous solution, but plus a particular solution. Okay. That homogeneous solution I have just got, okay, for the homogeneous boundary condition, okay, c by sin cube theta. What about the particular solution? Okay, the solution of the particular equation. Okay, it is any one solution of the inhomogeneous equation. Okay, it is any one solution of the inhomogeneous equation. So, how do I get that? Okay. I have this equation 3 by 2 P e into cos theta delta cubed plus sin theta by 3 d delta cubed by d theta is equal to 1. Okay. Alternatively, I can take this Peclet number to the right hand side, okay, and write this as 2 by 3 Peclet number, okay, just rewriting the equation. Okay. So, this is for the particular part. Okay. It has to solve the inhomogeneous equation. How do we solve it? We write down delta particular cubed is equal to delta homogeneous cubed times an integrating factor. Okay. We write this as particular solution as the homogeneous solution times an integrating factor. The equation in terms of this will become cos theta delta h cubed delta f cubed, okay, plus sin theta by 3, okay, into d and these two terms cancel. Okay, you can easily see that because those were the solutions of the homogeneous equation anyway. Okay, so these two terms will cancel. Okay, and what I will be left with is a solution, is an equation of the form sin theta by 3. Okay, delta h cubed, okay, is 1 over sin cube theta, okay, times d delta f cubed by d theta is equal to 2 by 3 Peclet number. Okay. That is the integrating factor that I have used, okay, in order to get the solution. Okay. So, therefore, this 3's will cancel out and I will get d delta f cubed by d theta is equal to 2 sin square theta divided by the Peclet number. Okay. And this gives us a solution, okay, delta f cubed, okay, is equal to theta minus sin 2 theta by 2, okay, times 1 over P e. Okay. I have to just integrate this, write down sin square theta as 1 minus cos 2 theta by 2 and then integrate it. 1 minus cos 2 theta by 2 will give you theta minus sin 2 theta by 2. Okay. This is a 1 over Peclet number, okay, which means that delta f cubed is equal to theta minus sin 2 theta by 2, okay, times 1 over P. Okay. So, this becomes plus, okay. I have to, in order to get delta P, I have to multiply delta h cubed times delta f cubed. Okay. So, I will get 1 over sin cube theta, okay, that is delta h cubed into theta minus sin 2 theta by 2 into 1 over the Peclet number, okay, that is this term here. Okay. So, let me rewrite that again after we have got the solution. Therefore, delta cubed is equal to c by sin cube theta plus 1 by sin cube theta into 1 by P e into theta minus sin 2 theta by 2. Okay. That is the boundary layer thickness cubed. How do we determine the constant? We have to determine the constant from the condition that at the upstream section, okay, at the upstream end, okay, at the upstream location where theta is equal to 0, theta is the angle from the downstream axis, okay, theta is the angle from this upstream axis. Therefore, at this upstream end where theta is equal to 0, the boundary layer thickness has to be finite. Okay. Determine the constant from the condition that at theta is equal to 0, delta is finite. If you look at the second term here, okay, it is 1 over sin cube theta. Okay. As theta goes to 0, this goes as 1 over theta cubed, okay, times a 1 over Peclet number, theta minus sin 2 theta by 2. Okay. If I expand it out, this is, okay, theta minus, okay, sin 2 theta is going to be equal to 2 theta minus 2 theta the whole cubed by 3 factorial plus etc. That is the whole thing divided by 2. Okay. So, this second term here, these two will cancel out, okay, and therefore, the numerator as well is proportional to theta cubed. Okay. The numerator is also proportional to theta cubed, okay, and therefore, this term is finite. Okay. If c were non-zero, this term would be infinite at theta is equal to 0. Okay. So, the only way that the boundary layer thickness can be finite is if C is equal to 0 at the upstream end. Okay. Therefore, C has to be equal to 0. Okay. And the boundary layer thickness delta will be equal to 1 p power minus 1/3. I have to take a 1/3 power of this 1 divided by sin theta into theta minus sin 2 theta by 2, okay, whole power 1/3. Okay. Note that the boundary layer thickness once again goes as Peclet number to the minus 1/3 power. That is no surprise. At a solid surface, the velocity has to decrease to 0. Okay, therefore, the velocity has to increase linearly. Convective term is proportional to the velocity times the streamwise concentration difference, and the diffusive term goes as 1 over delta square. So, that gives you a P e power 1/3. And then there is this dependence on the angle theta that we have explicitly calculated for the boundary layer thickness. This is finite at theta is equal to 0. It is not finite at theta is equal to pi. Okay, the downstream end, this is not a finite velocity. Okay. Okay. Note that my boundary layer thickness was of the form delta of theta is equal to 1 over sin theta Peclet number power 1/3 into theta minus sin 2 theta by 2 whole power 1/3. At theta is equal to pi, this thing goes to infinity, and that is why when I initially drew the boundary layer, I was careful not to extend it to the downstream section, because at the downstream side you have a concentration wake where the boundary layer thickness goes to infinity. In this particular case, when the boundary layer thickness goes to infinity, the assumption that we had made that delta is small is no longer valid. Okay. And it turns out that you have to solve for the concentration equation within a thin region in the downstream section. Okay. And in this section, you have to make the approximation that this angle from this downstream axis is small. Okay. You have to make the assumption that the angle from this downstream axis is small, and then resolve that equation to get the details of the velocity profile there. So, this particular expression is not valid near theta equals pi, because it predicts infinite solution. You have to redo the problem at the downstream section, and that is the reason for the formation of a wake in the concentration behind the particle. Okay. Because near the downstream section I have a stagnation point, the velocity goes to 0 once again at the downstream axis, convective effects once again go to 0, and therefore, diffusion extends all the way into the fluid. Okay. It turns out that for calculating the flux itself, we do not really need to do that. Okay. The flux is well represented by this, because even when the boundary layer distance goes to infinity, the flux just goes to 0. Okay. So, the flux is finite even though the distance is going to infinity. Okay. So, I can calculate the average flux, okay, by integrating this over the entire surface. Okay. The average flux J average is equal to, okay, integral, okay, over the surface. We know that the surface area in a spherical coordinate system is r square, okay, r square sin theta d theta d phi. Okay. In this case, theta has to be integrated from 0 to pi, and phi has to be integrated from 0 to pi, okay, of the flux at the angle theta, and I have to divide by 4 pi r square, which is the area. Okay. So, inserting that into this expression, okay, the average flux that I will get, okay, at eta is equal to 0 will be equal to d into C naught minus C infinity by r, okay, 3 power 2/3 by gamma of 1/3. Okay. I have 1 over 4 pi. Okay. The r square in these two will cancel out, okay, in the expression for the average flux. Okay. Okay. Integral 0 to 2 pi of d theta, integral 0 to pi of I am sorry, integral 0 to 2 pi of d phi, okay, the meridional angle. Okay. d theta sin theta, okay, into this boundary layer thickness. Okay. Peclet number power minus 1/3, sorry, I should have 1 over the boundary layer thickness. And I have a sin theta on top, the expression for the boundary layer thickness. Okay. This one is just 1 divided by this boundary layer thickness that I had, okay. 1 over delta, okay, basically comes into this angular integral. Okay. And you can do this integration. Okay. I will not go into the details of how the integration is carried out, but this integration can be done. And if you go through and do the integration, you get an expression for the average flux. Okay. J bar will be equal to d into C naught minus C infinity by R, okay, times a constant factor. Okay. All of these functions, okay, will go into the constant, and this integral, the integral over theta will also give you a constant value. Okay. And if you do all of that, you will get this as 1.25 divided by 2 roughly. Okay. Okay, this will be the expression for the average flux. And the Nusselt number is equal to J divided by d into C naught minus C infinity divided by the particle diameter. Okay. And I also have a factor of Peclet number to the 1/3 here. Okay. This comes out of the Peclet to the minus 1/3 in the denominator. Okay. And if I do all of that, I will just get this as 1.249 actually into Peclet number power 1/3. Okay. So, I have got the boundary layer thickness for you, calculated the flux locally at each angle theta, calculated the average flux, and from that I have managed to get an expression for the Nusselt number for the flow around a spherical particle. I will continue this in the next lecture for other configurations. Falling film we had already done before when we did similarity solutions. I will revise that briefly and then show you how that can be extended to other situations as well. We will continue that in the next lecture. We will see you then.